started?
Sure, go for it.
Kaveh, is Kaveh there?
Yes, I'm here.
Kaveh, okay, we can hear you loud and clear. All right, I'm going to get started, and Justin, will you just turn the slides? Okay.
Will do.
Okay. Hopefully everybody can hear me. I am here today, I don't know why I'm here today, actually, to talk about, we have a project, the coalition has a project called the Volume and Turning Movement Project. It was money and grants that we received from the Federal Highway Administration to look at the overall game plan was to see if we could take program states by, which is typically gives you speed data, and use something called GPS traces to look at estimating actual volumes, so you can get real-time volumes. So the idea, the long-term goal is that you would buy a probe data layer, like you buy TomTom data, you would eventually buy a license to get volumes as well in one procurement. So that's the long-term goal of what this research was doing. Okay, you want to turn the slides, Justin? So today I'm going to give you the overview and the background, and then I'm going to turn it over to Kaveh Sadabadi, who is one of the senior research fellows or assistants at the University of Maryland, who's the lead on the project. And he's going to talk about, we purchased the data set from New Hampshire from INREX and did some analysis on it to show you how we were able to estimate volumes eventually in real time. So, and then we'll have questions afterwards. Alrighty, so I think when we look at this slide about why do we need more and better volume data, you go to planning folks, and then you go to operations folks. And operations folks will tell you, we want to have real-time traffic data. We don't get it. It's usually archived. It's historical. We want to have volumes here that's during inclement weather. You'll see there was a research that was done where all of a sudden they were studying the volumes, and there was a massive spike in the volume data. And it turns out eventually there was a weather event that impacted the data. Okay, so we're trying to get more real time so we can see what's going on. Performance measures. A lot of the states use this for MAP 21, and then obviously one of the investigators, Kaveh is out of the University of Maryland. Stan Young, who was the original architect of what we call the VPP, which is the Vehicle Pro Project. He was the original. He moved to Colorado to become part of the National Research Renewable Energy Lab, which is part of Department of Energy, DOE. So he kind of moved during this project. So he has also been still one of the co-PIs, but he's looking at it more from an energy assessment standpoint. There's lots of insurance companies and folks like that that are looking for real-time volumes. So that's from his component. So next slide. There we go. So what this shows you right here is, I think, the overall goal. What you're seeing are two slides. On the left is they're both actual schematics of the Colorado area, because there was an initiative done with Stan's group with TomTom in the Colorado area. On the left, the 14 little yellow blue dots really represent their counters, their reliable counters. And eventually, the goal is to say if we can use probe data to get to more of a ubiquitous network on the right, so you'd be able to see volumes everywhere, not just in those particular locations. So basically, I can't necessarily read what the bottom says here, but I think that the idea is to fortify your existing network, and so that you can see data in arterials, you can see it in other ways, and this is one of the best alternatives we've seen. Okay, next slide. Kaveh's going to go into a little more detail on how they did this, but this is kind of the proposed solution of how they built the modeling to get these volume estimates. They take the input side, is where probe data is kind of the key of what they use, but they're also using in their machine learning and their modeling road characteristics, geometry, up, down, curves, etc. They're using weather information, and then the temporal data is like month, day of week, time of day. Okay. So they throw all these inputs into that estimator. They use a lot of machine learning. Colorado is using a kind of a methodology that's different from NREL, but they're using that calibration network above to map to it and make sure that the data makes sense. So they use two different machine learning methods with different algorithms, and then the calibration network above, which was those counters. And he's going to explain that, how they work with it, how they do 13 iterations, and then the 14th iteration has a special station with it. He'll explain that. But the end game then is to provide output that has traffic volumes everywhere and all the time. So this is kind of my high level, because I know enough to be dangerous. I know enough to be dangerous. He's the guy that's going to tell you a little more about it. The other thing that's important to know when you look at this is they had to figure out how good was good enough when they took the data. So if you're a traffic engineer, so they're using three kind of core metrics here, and their data, they're looking at metrics. If you're a traffic engineer, you kind of want to look at the MAPE, the absolute percentage error. If you're a statistician or a planner, you're interested kind of like in the R squared. And if you're a highway operations person, maybe the error to capacity or maximum flow. Those are the kind of the metrics that they were using. And basically, the MAPE, which is really kind of volume dependent, you're finding that if you had a high volume roadway, if your MAPE was in the 10 to 15% range, you were getting good results. 20 to 25% mid volume and low volume, and it's not, you're not going to see it today, but Colorado did do, Maryland did a volume analysis on high volume roadways, and they got great results. And then the next step was, well, what about low volume roads? Colorado did an analysis on the low volume roads, and we're getting great results as well. You're only going to see the Maryland analysis today because they were the ones that used the New Hampshire data set.
What do those percentages represent?
Percentages where?
10 to 15%. 10 to 15% of what?
What volume accuracy of volumes, estimating a volume estimate. If you took a counter and your counter had 1,000 volumes vehicles per hour, and then you used this methodology and you got what, 900, you're within that 10% range. That's what they're talking about there. And the coefficient of determination, the higher the better. And so the error to capacity. That one was interesting because when they started the project, they did a survey of planners and operations up and down the corridor. And a lot of them came back and said, if you can get within 10%, then let's run with it. There's some value here. We're actually coming up with 5%, less than 5%, and they're trying to get it lower for accuracy. So those are the metrics. So when you see some of these numbers and you're looking at them from a standpoint, that's what we want to put up there. Okay? Go ahead.
We type our questions in the chat box. I mean, probably for other people.
You can, absolutely, because we can't see the chat box here.
Yeah, I was just thinking.
So this is Kaveh. I'm going to turn this over to Kaveh for a second. Kaveh, he basically is a senior research faculty person at the University of Maryland. Got his PhD from the University of Maryland, but also, other, I don't know where he went. Where'd you go, Kaveh?
University of Texas.
Texas, yeah, I thought so. And he's got like 15 years.
You can tell by his accent.
I can tell by his accent, absolutely. Dan, are you on the phone?
I'm listening in. Yeah.
Stan is also the other, I didn't think he was going to be on the phone today. He's the other co-PI. He is actually the original architect of the VCT. And then he moved. So Stan, anything that I said in those first 6 slides, you have to correct me if I said it wrong. Does it sound okay?
Sounded great to me, so I'm good.
All right. Okay. So I'm going to turn it over to Kaveh, and he's going to talk now. One of the things important before he starts to know is that we had the opportunity to select different states to buy data sets to do this analysis. So University of Maryland had been working with INRIX. They have a Maryland data set. And then we looked at the demographics, we looked at the area, and we chose a small state. The contract called for less than 5 million and greater than 5 million. We chose Florida, and then we chose New Hampshire. Okay? And I think that there's some rationale for what you'll see and what we were able to do with the data set, comparing it with Florida. But know that that's by design. We chose this state, okay, and bought the data set. We can share the results with you. We're not allowed to share the core data, but we can share the results based on the work that's been done. Okay. So Kaveh, go ahead. With that, I'm going to turn it over to you, and I'll shut up.
All right. Thank you, Denise, and thanks everyone for tuning in this afternoon. So yeah, my name is Kaveh Farokhi, and I'm going to present the results of what we did on New Hampshire data set, as Denise was describing earlier. The technical work is done by 2 of my colleagues, Przemysław Sekula and Zachary Vanderlaan, who both of them are also on the line. Just wanted to thank them, and I'm just presenting the result of their work. So let me move to the next slide. Just quickly, an outline of the presentation today. I'm going to provide a quick overview of the project and objectives and how the volume estimation approach, even though Denise already did a good job doing that. But I tried to spend more time on the New Hampshire case study and the results that we got from specifically our analysis on this data set. I'll talk about the performance of our model at continuous counter stations, and also I'll talk about the statewide estimations that we did, also the work related to transferability of models from other states and other data sets to New Hampshire, and at the end I present a couple of slides on estimates that we got for annual average daily traffic, and also the flags that we developed in combination with our estimates. And at the end, I wrap up, and then we can spend some time on question and answer. So, as Denise said, the objective of this work is to see if we can build a model to accurately estimate the statewide volumes given probe volumes, which are basically trace data of a subset of vehicles that are moving around on the roadways. This data became available lately. Vendors like InRigs or TomTom and a couple of other vendors have opened up their resources and provided this data sets to whoever is interested and is able to pay for it, basically, and license it. And we want to combine that data with other archive data that we have access to. Denise mentioned the speed data from Vehicle Pro project, road geometry data, number of lanes specifically, weather data, and et cetera, et cetera. And at the same time, we need to have continuous count data at select locations, namely at ATRs or continuous counter stations. We use that for calibrating our model, and once we have the model, then hopefully we can estimate volumes at other locations that we don't have any counter stations. So this is basically the general approach. Like any other modeling technique, we need to first develop and train the model, and then in the next step we apply the model to, as I said, other segments of the road throughout the state. In the first step, as you see, probably the maps are a better way of describing this. In step one, the map to the left of the slide shows location of the counter stations. So we do the training and calibration and testing on volume coming from those specific locations that we have real-world measurements from. Then, once the model is finalized and calibrated, we take the model and then we prepare the input data for all the other locations, and then we run it through the model, and then we generate the output for the rest of the network. So we will be able to build the map that's shown there, the whole network basically, on the right side of the slide. So that's the general overview of the process that we're going to discuss today. In terms of the New Hampshire data set, it was 3 months of data. Basically, summer of 2017 is included in the data set. It included 7 million trips, and it translated to 595 million waypoints. The penetration rate that we calculated at those counter stations, in terms of median, is just over 2%, 2.3% to be exact. And as I said, we combined this with probe speeds that are already archived in RITIS through VPP, and also road characteristics, number of lanes, speed limits, facility types, and etc. Also, we got access to archived weather data and other features that we can use as input in our model. So we put everything together at the first stage in preparation of model development. Looking at the data set in more detail, we found that just less than half of the trips that are reported in the data set are coming from cars and light-duty trucks. So that 46% that you see in the pie chart in the middle of the slide is representing the share of cars and light-duty trucks in the whole data set. And medium-duty trucks and heavy trucks, heavy-duty trucks types 2 and 3 comprise a little bit more than 50% of the data. And the heat map to the right also shows the distribution and density of the waypoints throughout the state, and also the outside. Note that some trips that originated and ended outside the state are also reported as long as at least one waypoint of the trip is falling inside the New Hampshire. So as you see, there are a lot of trips that go through 95, start and end outside the state, but still are reported on a part of the data set. Just to put everything into perspective, I provided a little bit of information on the Florida data set, which was from fall of 2016, quarter 4, 2016. It was comprised of 75 million trips, so almost 10 to 11 times larger than New Hampshire data set, had 3.4 billion waypoints, but interestingly, the penetration rate is about the same. The median is, again, just over 2%, and also the distribution of the counter stations in Florida is shown in that small map to the bottom right of the slide. So looking at more details of the model estimation, model calibration process, and the results that we got. In New Hampshire, we had 42 continuous counter stations that we got data for and we used in our model training. So the approach that we took was, this is called cross-validation, and we're trying to estimate a dense artificial neural network model. Neural networks are well known in the field of machine learning. They are very well researched and described in the literature and are used for a lot of modeling activities these days. So what we did in terms of cross-validation was to take one of the counter stations and leave it out in the whole process of training, and do the training on the other 41 stations. Once we had the model, we would test the performance of the model on the one that we left out. So that way there is no ambiguity in terms of what data is used in training and what data is used in testing the model. And then we repeated this 42 times. So every single counter station has been left out at least once, and the model that was tested on that particular counter station was trained based on all the rest of the data coming from the other 41 counter stations. So that was the approach that would guarantee that there is no, so to speak, cheating in our model training and calibration. If you look at the result of this exercise, that graph to the right of the slide shows the real volumes versus the estimates of our model. Ideally, if model is perfect and whatever we estimate from the model is exactly equal to the real counts, then everything should fall on the diagonal line but obviously this is a modeling exercise. There will be errors. So you see that point cloud that's formed around 45-degree line. Looking at it, it shows very good performance, especially if you take into account the fact that a lot of data points with more concentration and density are falling very close to that diagonal line. So that's why that color coding is showing darker, colors closer to the 45-degree line. And there's, as I said, consistent behavior on the part of the model in generating estimates that are close to the actual volumes. So in our modeling effort, we compared different type of models. We did different tests basically. So first, if you look at the table, the first row, the model we call Florida is a model that's trained only on Florida data, and we took that model and we applied it to New Hampshire, and the results that we got are reported, on the first row, basically. Then, what we call base model is a model that's only trained on New Hampshire data and applied to New Hampshire data. So, the results obviously are better. R-square of 0.83, MAPE of 28%, and error to maximum flow ratio of 7%. That's what we got when we looked at the base model. The third option was to take the Florida model but fine-tune it with New Hampshire data. That's what we call transfer learning. Performance in terms of MAPE improved. The other two measures are relatively the same, at least in terms of the median of the measures. But the last row in the table is what we really liked and we used in our further work, which is what we call extended model, in which we combine the two data sets, combine both New Hampshire and Florida data to estimate our model and calibrate the model and use it on New Hampshire data. You might say, R-square, got a hit a little bit, went up from 0.83 to 0.84, and also the MAPE went a little bit higher compared to transfer learning. But the point is, when you look at the box whisker graph at the top, you'll see the extended model has a smaller dispersion in terms of the error, in terms of MAPE. So even though the median went up a little bit, we are overall seeing much better performance compared to the other models. And that's why we picked the extended model. Okay. Digging deeper into the results, we looked at performance of the model on different road classes, FRC1, FRC2, 3, and 4. Also, we looked at different levels of hourly volume when you're looking at low volume segments and times. And as you go up to 2,000, 3,000 level, all the results are reported here. And also, we wanted to see the average number of probes per hour. We're getting from the data that we licensed from INRIX how it impacts the results. So we looked at the low average probe counts to medium probe counts to high probe counts per hour at 3 different categories, and looked at the performance of the model in each subcategory. Overall, the median error metrics are as follows. R-square is 0.84, MAPE of 27%, and error to maximum flow ratio of 7%. Interestingly, as you look at the tables and the numbers that are reported here, the accuracy of the model goes up with the road class, with the average hourly volume, and also with the average hourly GPS counts. So in general, this is consistent with expectations. So as we get more probe counts in our data set, the correspondence and correlation between that information, the number of counts, number of probe counts, and the actual count of vehicles in that hour goes up, and that's to be expected. So that's why the arrows are all pointing up. On this slide, that accuracy is best when if we are looking at freeways, for instance, or highways of higher road class, and when you're looking at peak periods, for instance, the performance is better than when you're looking at overnight or off peak, and so on and so forth. So up to now, what I showed you was results of model performance on continuous counter stations. Now we really get to the point that we needed to show that this model can be applied to the full network, and we can generate estimates for all the other locations, all the other times. So New Hampshire network has about 2,000 TMC segments, and we prepared the input data for all 3 months of for which we had the data, and then we ran it through the model and we generated results. And there's an animation that Justin is going to show. Yeah, so this shows the hourly volumes and its dynamics, basically hour by hour during that 3 month period. So as you see, the color coding indicates that you'll see higher volumes in main corridors throughout the state and also in urban areas, which is consistent with our expectation. Obviously during peak hours, the volumes are going up, and during off-peak and overnight hours, you'll see more bluish, color shades throughout the state. And as you look at the urban areas, as I said, you will see, changes over time, but in more rural areas, pretty much everything stays the same. There's not much variation over time, even though we are still looking at pretty high level roads, in this map. Thanks, Justin. So we managed to estimate hourly volumes, but still in a lot of planning and project engineering applications, we need to have estimates of annual average daily traffic and annual average weekday traffic. But since we have the hourly volumes, it's a very simple exercise to aggregate those numbers to the average daily values, and that's what we did. So these two maps show the AEDT and AWDT estimates on all those segments throughout the state. And the measures that we're reporting here in terms of the error, in my opinion, are very good. And since we did the aggregation, please note that these measures are even better than the measures we got for hourly estimates, because the errors tend to cancel each other out when you sum them up and take the averages. So R square in the order of 0.86, 0.87, and MAPE of 17% or 18% are really good for this kind of volume estimation. And as Denise mentioned, the results are available. If needed, we can share that with you. Also, just to make sure that we provide another layer of information to the end users of our estimation work. In addition to the actual hourly estimates, we will generate two types of flags to indicate whether input data to the process, to the model that estimated that number, is in fact normal, and we try to flag any unusual behavior on the part of the input data and also on the part of the model estimates. So in terms of the number of GPS counts, let's say if it's Wednesday, 9 a.m., one particular segment of the road, and you expect 10 GPS counts for that hour, but you get 50 GPS counts. We wanted to flag that as something abnormal, and if the expected volume for that particular segment, particular hour of the day is, let's say, 1,000 vehicles per hour, but you get 200 or 5,000 vehicles for that segment as an output from the model, we wanted to flag that. So we used averages and standard deviations around the average to flag those scenarios. This could be indicative of very interesting events on the road. It could be a result of an accident. It could be a weather event. It could be a concert. It could be a sporting event. So this additional layer of information can be very helpful for the end user, especially in operations, to be able to pinpoint locations and times that something abnormal is happening, and they can probably look at the details and figure out what's going on in that location and time. So that's the value for this type of flagging activity. Just to summarize and wrap up, we basically managed to estimate hourly volumes, and we showed that our estimates meet requirements for most planning and operational purposes. And of course, I argued that the quality improves with the road class and the actual volumes on the road. So as number of probes increases, and that's something that we've seen over the years, that the trend is always upward in terms of the number of probes. We expect this estimation quality even get better and improve over time. So right now we are working with a data set that on average pretty much has 2% penetration rate, but if it gets to 5% or 10% penetration rate, we would expect even better estimate, better results. In terms of model transferability, I showed that it's possible to transfer or fine-tune the model from other states, and in general, having access to data from other geographies, other jurisdictions, and even from different time periods, it's very valuable in training and calibrating new models for any specific location. ADT and AWDT estimates, we generated estimates with very high level of accuracy, and results are consistent with expectations along major highways and urban areas. In terms of freight volumes, we developed a methodology already, and all it takes is to have access to freight counts at the same continuous counter stations that we use for training. But we did this for Florida. In the case of New Hampshire, if we get access to such data, we can also develop models specifically for freight count estimation, and we can provide the data to you guys. In terms of flags, methodology is developed and applied to the Florida data set, and we expect it to work very well also for New Hampshire, and we are already in the process of developing the results of the flags for New Hampshire as our next step. With that, I thank you, and I give it back to Justin or Denise.
Kaveh, I think there might be some questions in the room.
Sure, yeah.
This is Susan from New Hampshire.
So what I think I'm hearing is, sorry, it's a little technical for me, but what I think I'm hearing is we have permanent count stations in New Hampshire that collect traffic volumes. If you combine our permanent count stations with probe data that we are purchasing, is there a way to reduce the number of either 3-year count stations that we do for reporting, or to reduce the number of motor vehicle protection sensors that we put up? But the reason we put up our MVDS is really for the volume piece. We're capturing the speed through our probe data. So we really are putting those up to capture some volumes. It's like, how close are we to being able to reduce the number of MVDSs, or the 3-year count stations that are done? Is there a way to reduce those? I have no idea. I think I heard that, but I'm not really sure.
They're using those count stations to model.
But they're using your permanent ones, the 24/7, 365 ones. They are not using your every 3-year ones, right?
That's what it sounds like, yeah.
That's what I'm wondering.
Yeah.
And how close are those volumes that they received at those locations to your 3-year station? You know what I'm saying?
Yeah, right. How close are we to realize an opportunity to reduce some of our count program?
Exactly, or reduce some of the MVDSs we're putting out, quite frankly, all over 93. Right. Did you hear that, Kaveh and Stan?
Yes, yes. Let me make a comment. We actually did a test on a New Hampshire data set, actually specifically to be able to answer exactly this question. So what we did, we started with Florida model, and then we started adding data from New Hampshire every 2 weeks, meaning that we added only 2 weeks of data, then 4 weeks of data, then 6 weeks of data. The results showed that by adding only 2 weeks of data, we can pretty much get very good estimates from this model. But given the assumption that we have access to Florida and a really good model already. So the answer is yes, it is possible, but it's not just using that 2 weeks of data that's going to solve the problem. You need to have an existing good model that you can retrain or fine-tune using your short-term counts. So what that indicates is that yeah, there's a huge potential for managing the permanent counter stations or short-term counter stations better. Reducing their number probably is one option. The other thing is if you can use a smaller number of short-term counter stations, but move them around throughout the state once in a while. Every month, take them from this area to the other area, and so on and so forth. So it opens up a door for making better use of existing resources, or managing them better, or optimizing the number of counter stations that you use for your data collection.
Do you have to be a member of RIDIS?
Yes, I am.
No, New Hampshire is not a member of RIDIS. And I saw your input was information from RIDIS. Do we have to be members of RIDIS in order to use this model?
Can I cut in on that, Denise?
Yeah. Go ahead, Stan.
Yeah, there's a comment earlier I almost jumped in on. The data that's used to create this goes beyond what is typically procured through the Vehicle Probe project and what is available in RIDIS. particularly you have to work with the vendors to get the probe counts, and we're in that discussion now. It's another item of data that they can provide that is currently not in their speed and travel time. That being said, in order for all this to work, we also in addition to these probe counts, we use an indication of speed at any point in time, which is usually given by the RITA system or some type of contract with a probe vendor. I think New Hampshire, aren't you guys using TomTom data or have a contract for TomTom data with respect to speed and travel times?
That and some NREX.
Okay, got it.
Yeah, we have TomTom, we have NREX, and we also have physical sensors, all that are feeding our system.
I was also going to comment on the other question about, I don't quite get the lingo with the counts, but I know NREL did a parallel study with Colorado DOT, and once we got off the freeway system, there was no data from permanent counters, continuous counters, so we used 48-hour counts. I think they're similar to what you're talking about, where they rotate count equipment around periodically, and we're able to get consistent good results with that as well as a calibration input.
Dan, there's a question in the chat box about, in terms of the statewide travel, can the model report travel on a weekly, monthly, or annual basis? Did you see that in the chat box?
Oh, yes. Okay. I think both Kaveh and I can address this. When we started this, we were somewhat operations driven, so we were driving it down as granular as we can. So right now, the base outputs of the model is, here's the estimated volume for any hour of the day, any day of the week, any week of the year, 24/7, 365. We have since then saying, hey, sometimes you want this, what you said, weekly, monthly, or annual, and we can aggregate it at any level. Kaveh's done AADT estimations with great results. We've done something similar. So we can support reporting at any one of those levels of granularity.
So that talks about generalizing the numbers. What about getting more specific in segments between interchange ramps by hours of the day? So if we want to plan for lane closures and so forth, we know what the volumes are at that location. Also, as we look at operation strategies like shoulder use during peak travel times or ramp metering, and want to measure the effectiveness of those strategies, how granular are we going to be able to get with this data?
Right now, we're at the segment level, as you said. If you're familiar with traffic message channel codes, those come from NRIX. That's what UMD used. They're typically, I don't know, I think about a mile long. We worked with the TomTom has an equivalent segmentation. So as far as spatial granularity, I believe we're already there. The time granularity, we're working right now, the best we can support is 1 hour basis. This is determined primarily by the data granularity we were able to obtain to create the models. We would like to, an effort, push that even greater in time. We think we could probably get to a 15-minute rolling window for freeways with moderate capacity and above. Once you get down to off-freeway results, I think it would be hard to support anything, possibly go from an hour to a 30-minute rolling window, but doubtful you could support anything greater than that. And that's all dependent on having the base input data feeds also at those levels of time granularity.
Yeah, and just so I understand how this works, you have about 2.3% of the vehicles have the probe information that you're mining, and then you're using that percentage of probes with the total counts from the count stations, and you're building algorithms to use your machine learning or training to boil this all down. Is that close to what you're doing?
Yeah, that's a very good analogy. Working with the NRIX data, they get about a 2% sample, And in essence, we're factoring that up, but we're trying to do it as intelligently as possible with a calibration data source and a lot of other data sources to help fill in the gaps when that's inadequate. That percentage does change with vendor. We've seen it range from 2% up to 10% in our work, so that is also something to take note of.
And Stan, isn't the TomTom, is the 10% is the higher end, correct?
Yeah, that's where we saw 10% in the Colorado, specifically Denver metropolitan region. It varies by vendor. It also can vary by geographic location as well. It's something that we're learning.
So what's the 2.3% penetration that was referenced in the presentation?
That is the, I use 2%, but that 2.3% specific to New Hampshire, that is that penetration rate, the percent of all traffic that NRIC sees. Did I get that right, Kaveh?
Yeah, that's the median. It varies probably between 0 and something around 7-8%, but 50% of the time it's less than 2.3%. 50% of the time is more than that. So what I reported there was the median, is right in the middle of the spectrum of penetration rates.
So that's the percentage of probes that you have out there, and then you know how many of those probes are vehicles, light trucks, and trucks, and that's how you're getting your freight numbers? Are you getting your freight numbers as a function of your counters and your probe data? Because frankly, if the freight numbers look a little high, so I'm trying to understand where that's coming from.
They're looking at in the pie chart, the percentage when you looked, the percentage had about 46% of medium to light duty trucks.
Cars to light trucks are 46%.
Cars to light trucks are 46%, which meant the 53% was the rest of the stuff.
Yeah, that's the distribution of different vehicle types in the raw data set that we got from INRIX. So, INRIX is reporting 46% of the trips during that 3-month period coming from cars or light-duty trucks, and 36% coming from medium-duty trucks, 18% coming from heavy-duty trucks.
It's the 18% heavy-duty trucks that sounds high to me. That's a number that, Mike, if you're familiar, you're probably more familiar with that. Are you what we usually predict?
That was the same thought that I had.
Yeah.
So
so the question is that a function of your probe, your 2.3% of probes, where you know that the vehicle with a probe is one of those classifications, or do you get that classification from the sensor data that we give you, or do you use both and you're using your algorithms to fine-tune it?
Very, very much the former. It's a uniqueness of the INRIX data feed. They collect data from a lot of telematics firms, which are associated with various shipping and freight companies, and so if they have data from a certain telematics firm that's serving long-haul trucking, it gets a tag associated with heavy-duty vehicles. If they have a telematics firm that's typically distribution of freight within an urban area, that'd be medium, things like that. They're not hard classifications from a sensor by any means, but more of a association or correlation that INRIX provides an indication of.
Yeah, so that's going to skew your data, because the motor vehicle drivers using their cell phone, I don't know if that's feeding, and they're not using TomTom or pay for service, or, I don't know. It's high anyway. It's skewed from somewhere, I think, but I don't know where.
I need to drop off the call now, Denise, due to another meeting. It's been great listening in and hearing the conversation, so let me know if I can help in any way.
All right, thanks. Kaveh, do you have any comments on Dave's question? And Chris,
no, but the only thing I can add is that even though there could be some biases or underestimations or higher representations, in the input data, the machine learning algorithm is capable of sort of adjusting for it, because we're using a lot of data to train the model, and you see a lot of examples of what the input is and what the output should be. So it learns over time, and it adjusts for the fact that some type of vehicles might be underrepresented or overrepresented in the data set. So it's very stable in terms of working with data that's not perfect.
Kaveh, there's another question in the chat box. What calibration was used to verify individual segment traffic counts? Did you see that question?
Yes. Is this specific to the neural network calibration?
Ask that again. You mean
Yes.
Calibration? Do they mean artificial neural network calibration?
the AND model? Yes. Yes. Yes.
Oh, okay. We use the standard calibration techniques. Of course, there are some parameters and some specifics to the type of neurons that we use and other things. I can ask Perjamek to provide more detail, probably in the chat box.
Are any other states or agencies using probe data and hard inputs in some model to get volumes such as this?
Kaveh, you want me to answer?
You guys are the only ones starting this.
Let me. I'll answer it, Kaveh. The project right now had a phase 1, which is can this work? Does this do we get good enough numbers to make it work? So now, yes, the next step is to bring it to operationalize it, as a product. So we've had discussions with, obviously, Colorado, Kansas, and Nebraska out west. But we've also talked with Alabama, Florida, Georgia, Virginia, Maryland. We had a call with the Port Authority of New York, New Jersey today. You guys, tomorrow is PennDOT. So there is a massive amount of interest in how do we get this to over the finish line to get it done. And so Stan, who's no longer on the call, has been working with the vendors. TomTom and INREX have both agreed to and working on a licensing component to be able to say, if you want volume estimates, you want real-time volume estimates for your state, this is the amount of money it's going to cost you. There's a line item, and you're buying probe data, you get a center line per mile cost, but then you want volume estimates, so it's another modular. He's in the process of doing that. Here it's decided to take this methodology and bring it in-house to basically create their own type of product, okay, which is a little different. But so the INREX and the TomTom are all ready to work with these guys on finding an operational product.
Do you know if HERE's already released that?
No, they have not. They have not.
Hey, Denise, this is Trish. I kind of joined a little bit late.
Oh, hi.
And I just wanted to kind of pull us back. Maybe you did this at the beginning of the call. So just to clarify what the coalition did here is, so we went after a grant to push that bleeding edge of filling this need of volume. We need it for operations, we need it for planning, and everything in between. So what we did through this grant work that we won on behalf of our members is the results you see. And we picked New Hampshire because we wanted to have a state that had less volume to test to see if this concept could work in the real world. So the coalition bought special data on behalf of New Hampshire and conducted this analysis for you guys to give you hopefully something you haven't seen before. So this kind of statewide volume and more comprehensive on different functional classes. So hopefully all that is exciting. It's exciting for us because we see the need from our members for volume information. And as Denise just said, what we're trying to do next is see if we can have partners that can push this proven concept into operations. I'm also meeting on the federal side to see if they would support continuing to this type of grant work. But that's why we're excited to see these results and the great work that Kaveh and his colleagues did along with Stan. So I just wanted to make sure that that was clear as far as what we did and why.
Yeah, this is Susan. Yeah, Denise did go over that at the beginning. But to your point, Trish, you said something about that made me think. I typed a question earlier in the chat box about HPMS reporting, and it's interesting you just talked about the federal government. You know, what level of accuracy or what is needed for that type of reporting, and would this type of model be acceptable to them? Because the states still have to do that and get to some level of accuracy.
Right.
So I'm glad that you're talking to the feds about that, because that's sort of a key part for states, right?
Yeah.
Right. I think it's that, and the question is there a future where we don't have to have permanent or 3-year count devices in our system? So that's the idea. Is are there other means that are less resource, dollars, and time intensive to provide the volume data that we need for our own operations and planning, as well as for those federal requirements? So that's, again, the motivation that's driving us. And yeah, I think the HPMS, how great would that be if they had another federally accepted option for providing that data?
Actually, absolutely, like
Trish,
free reporting.
in Maryland last week, Maryland is in the process of putting in a request to the Federal Highway to see if the work that they're doing here on these volume estimates can, any dollar amount that's being allocated to the HPMS work they're doing, if it can be reallocated to this project so that we can get over the finish line with this, and then they could use this modeling and this process to do their HPMS reporting. So there are states that are already asking that question as well.
And Kaveh, I feel like you have, shared with me, and I hope I'm getting this accurate, that, states like Maryland's one reason why they're pushing down that path is because they see the results from this model by combining, using the probe data in this manner. They're getting better results than their traditional estimation for HPMS. Did I make that up in my head, or is that what you've heard from Maryland?
No, exactly. The current process that they have to go through to generate their HPMS numbers, it takes time. They have to spend a lot of money on it, and at the end of the day, they use it for different purposes, for different decision making and reporting, applications. But they know that they can improve it, and that's why they are interested in our work. And they're already in the process of licensing a full year of data from INRIX for specifically this purpose, this project, and also other applications. Because once you have the trajectory data, the probe data with traces and so on, you can do a lot more. It's not just limited to the volume estimation. In terms of performance measurement, trip-based performance development and decision making, and building all sorts of OD tables and whatnot, they can use that. So they're aware of it, and that's why they're interested in this.
Any other questions, guys? Dave?
Just to state a point, you are trying to answer the question that we all have. One, yes, it would be nice to provide the HPMS data with less effort. That's certainly the question. But number two, operationally, the more granular we can get this data, the more targeted we can be with our operational solutions to help increase capacity and reduce congestion. So it's very good, and we like that the feds support this, because not only do they want the HPMS traffic volume information, of course they want the speed and congestion information as well, and that's part of what we have to report on for measures, and one system can do it all. So good.
And I think if we could get to the point where this approach to estimating volume can be used to better plan lane closures for a bridge repair, I mean, that would be fantastic. So that's the thing I think that's so exciting about this potential, is it can be used at more aggregate and disaggregate level. And so that's what gets me excited, is that potential there, saving people time, money, and coming up with more accurate information we can base decisions on. So it's exciting stuff.
Yeah, we had a discussion this morning with the Port Authority because they are a much more different beast than a DOT, and how you get to ramps and interchanges going through tunnels, how you do work zones particularly. This would be invaluable to them to be able to know what that data is, particularly in those tight confined metro area that they're in. Okay. Anything else from anybody on the line? Are we?
Thank you very much.
All right.
Thank you for your
Thanks,
time
guys.
and your effort pulling this together and for sharing it with us. It's great.
Thank
All
you.
right.
I appreciate your time.
Thank you.
Thank you.
Bye, guys.
Thanks.
Bye.